Well, it's time to get started. Couple announcements before we dive into our summary and new content. The first is that somehow, I don't know how this happened, we're halfway to our first exam already. So I wanted to briefly talk about what that process will look like leading up to the exam. I will be getting you a study guide a week before, so this Friday you can expect a study guide to be uploaded to Canvas. What I usually do for study guides is I give you a list of topics that we have covered, but I don't really give you a ton of information about those topics. I find that to be very useful study material to try to figure out, okay, what is that? But sometimes I will include questions or further detailed topics. And those kinds of questions would be something that I might pull directly onto the exam, or I might ask in a slightly different way, but it's to start getting you to think about the kinds of things that I might throw on an exam. Things to know about my exams, I, wherever possible, try to not ask questions that require regurgitation. If you can Google it in 2 seconds, I'm not interested in whether or not you have it memorized. I prefer to ask you questions that involve critical thinking or applying something that you might have memorized. As long as you understand the idea, I'm not concerned if you have the definition memorized. But if you have an intuitive understanding of what it is, then there might be a question that asks you to apply it to something that is similar to, but not quite the same as something we've seen before. So I like to challenge people a little bit to really have the concepts from class understood at an intuitive level rather than memorized for regurgitation. So because of that, I tend to minimize the number of things like multiple choice and true false, just because if you get it, you get full points. If you don't get points, you can guess. I don't generally like that as much. So you assume that there will be a significant amount of problem solving, writing, talking about your understanding of a particular concept or topic.
So if we have a question like the card one on the exam, will there be information saying that like the spades is the fourth in that set? It's like, how are we supposed to know that?
Yeah, I would probably have something a little bit more straightforward than this. I try to, whenever I write a question, think about what kinds of misinterpretations could students have. If that were to be the case in an exam, please ask me. Don't just make an assumption and run with it. That would be something that I would love for you to ask me during the exam to make sure that you've clarified it and that you're not making any assumptions on the exam.
Sounds good.
I will try to minimize the amount that is required, though. And then second, I'm making a very small, hopefully, in your favor, change to the assignment. In that I mentioned that when you have two different generic types, try to convert one to the other where possible. That is going to be a little bit more complicated than I think is really necessary for this assignment. I could see things like a double to an int conversion, an int to a double conversion, either of those to strings. But then you're doing a lot of, double dot to string and stuff that you're trying to figure out exactly what those types are. I still would think it would be great for people to implement that, but I'm going to turn that into extra credit on the assignment. Instead, what I'm going to actively be looking for is check the types. If the types match, then append one list to the other. If the types do not match, throw some kind of associated exception. That will be the level that is required for the assignment. But if you'd like to try to figure out as many different types as you could convert from one to the other, that would be cool to see. And I will look for it and give extra credit where I find it. Are there any questions about that? I'll try to make the updated changes to the actual text in the assignment. I will hopefully get around to that today. Anything else before we dive back into new content? All right, we ended last class talking about this example where we had some cards we were constructing a deck and we wanted to figure out how computationally expensive was it to actually create the deck. And so we went through the code line by line. We figured out how many operations each line was, and then how many times each of those lines were called throughout the execution of this constructor. And we found that as long as we make the assumption that both the ranks and the suits are scalable, then it was quadratic in the sense that we have ranks times suits in multiple places here. If we hold the number of suits constant at 4, then it turns into a constant. And we see this a lot in computer science. There will be a lot of back and forth about, is it linear, is it quadratic? Trying to assign a label to it is not quite as important as understanding how they do scale. So I would be much more, it's best rather than trying to say this is linear or this is quadratic, you can say that it runs in time proportional to the ranks times the suits. And that way there's no ambiguity. If we know that the suits are constant, then someone who reads that can think, well, that's basically linear. If the suits are scalable, then they can think that is basically quadratic. And you leave it up to the user to interpret that how they will, but you are still very technically correct by saying that the complexity here is the ranks times the suits. Yeah,
Is there a plugin or something on IntelliJ where you can like highlight code and it will tell you the time complexity?
there is not.
Really? No.
The reason is sometimes that changes and sometimes you have to analyze more than just that local, like what happens if this constructor is called in a loop? How do we know how frequently that is done? And actually, if you're interested in this, there is a whole section of the compilers course, a 400 level course, that will go into kind of the theory of computation and what we can and cannot write programs to do. And we can actually use mathematical proof to show what we can and cannot do, basically, as computer scientists. So that's a super cool part of that course. But that is not something that's very easy or scales particularly well to that code. It's not easy to figure out or to write a program to do in general. It's a great question, though. All right, let's see one more of these. We've written a program called Go Fish that is going to construct a deck just like we saw before. And we now know the complexity of the deck constructor from the last example. But now we might need to figure out, okay, how expensive is this shuffle method? Wherever it is not mentioned, just take a best guess at the running time based on what they need to do. So the shuffle needs to do some associated logic. Try to figure out if we were to implement this, what would the associated complexity be? But let's go ahead and attempt to assign the number of times that each of these are called and how expensive they are. And see if we can come up with an order for this entire Go Fish game. Just like before, work in groups. Share the knowledge.
But it's only gonna show. Yeah, these were the games, so it's the. Complex, it's the new jag, which is the. So I'm gonna check for 7. It's less. Yeah, right. It's 7 shots. Yeah,
Like your close card off the top, that's where you're doing this additional.
yeah, so if you already have your hand, it's either, you know, it's a little hand, which is not in, or which, the keeps one. I'm assuming this is the go fish hand, probably yours. So. If you're not adding it. The shuffle problem.
I think. We come to a consensus between the people you were working with,
You got 4 and plus 9.
4n plus 9. Let's take a look. So for the prior ones, I actually wrote this out. But here we go. We are going to, everything before we get into any method call is just done once. So all of these assignments are just done once. The deck constructor is called r+1 times s, not called, it's called once. But the process that we found from last class was that it takes r+1 times s operations in order to construct the deck. So we can just pull that logic out and apply it here. Shuffling the deck, in order to do that, we would have to do things like pick the first card, or pick the bottom card, pick the next card, pick the next card, pick the next card, pick the next card. So to try to figure out what that is, it's gonna be rank times suits number of operations. Just pick a random number and pick that card and put it in the appropriate position, do something like that. That would involve r times s operations. So shuffling would take, if we're using a standard deck, 52 operations. Then we're going to make a new go fish hand. That's just done once. Same with the player hand. We're not assuming that we're doing anything with this. So this add is what's actually filling the hand with something. So this constructor is really just making the object that will store the hand. It's not doing anything in a loop necessarily. So it's okay to call that just happening once. For this loop, we're used to a loop involving some kind of end because we don't know how many times it's going to run, or the number of times it's going to run will scale with the size of the input. But with this loop, it's always going to run a constant number of times. And we can tell this from the I is less than 7. That 7 being a constant tells us that there is a consistent size to the hand. So we don't want to scale this based off of n or any other variable because it's a constant. And this player hand and computer hand dot add deck dot deal is just going to pick one card from the deck and add it to their hand. So it's really only one thing that's going to be happening, but it happens inside of this loop that runs 7 times. So that is why this happens a total of 7 times, once for each pass through the loop. Questions on this? Yeah.
So like whenever you have like a list object, are you pretty much always storing a current so you can just if you're adding to the end of the list, it's always just like, oh, one.
Yes, so you would assume that if it's a linked list, you have a tail so that you can easily do that in O of one. If it's an array list, then you can always just add right to the end with a quick multiply. If we're using a linked list without a tail pointer, then that would also be the size number of times. But that would be inefficient for no reason. Usually you can store a single piece of data that prevents you from iterating over an entire list. That is very worth doing.
What's the additional step for the shuffle to make it 53 times, not 52?
That's a good question. A very good question, not one that I really thought about. That may involve, so this is pulled from our textbook, and I'm guessing that earlier on in the textbook, there is some kind of implementation where we actually see the shuffle. I can go look into that and figure out, maybe there is something like assigned to the top of the deck to something. And that way we would assign, like, here is the card that is on the top of the deck. It'd be like assigning the head to something. Or if we needed to store that for some reason, that would be my best guess as to what that additional one thing is doing. Usually though, if you see a +1 or something of the sort, it's not super relevant to the order. So they shouldn't change a ton. If this exact thing we're missing from something, it's in an assignment or an exam, it's not super consequential. Oh, I did have one more of these. All right, the sum of the elements of a matrix. Go ahead and talk this out, see if you can come up with the running time of this sum function. Yeah.
Since we don't know this one, this is where you use like 10 or something.
Yeah, now we would have the. Basically, we're gonna have the number of rows and the number of columns of the matrix. This one's not quite as long. Anyone think they have an answer?
Okay.
This is certainly quadratic. So we find that what we're really curious about and what's going to dominate this is the line that's inside of the nested for loop. This is what's going to get run the most times. And this really shouldn't just be considered to be n. That would be the case if this were a square matrix, but if it's rectangular, then maybe you want to specify rows and columns, and you would find that this is, rows times columns number of times. But everything outside of the outermost for loop is going to be done once. Everything involving the outermost for loop is going to be done for each row, and everything inside of the innermost for loop is going to be done for each row and each column, so each row column pair. And we find this to be a very common logic that has to deal with loops. Whenever you have loops inside of loops, we multiply. Whenever we have loops followed by loops, we add. Why does that make sense? So let's say that I could modify this code such that instead of this innermost loop being inside of the outer loop, I pulled it out and made them sequential. So that we did something for each row and then something for each column. This would be something like if you wanted to sum each row and then sum each column, rather than try to sum every single cell and come up with a single total.
Wouldn't be called quadratic. If you didn't have the nested for loop.
Yeah, so we multiply when we have a loop inside of a loop, because every element of this inner loop is done not only for every time the inner loop, but this entire inner loop is done from start to finish for each pass through the outer loop. So that is the definition of multiplication. Basically, we want to say for each of the first element, we want to do all of the second element. If you were to try to do something like draw out a table that represented something like, I don't know, 8 times 6. You would say for each of 8 times, do something 6 times. You could, make a tally of 1, 2, 3, 4, 5, 6. And that's the first element of this. And then 1, 2, 3, 4, 5, 6. That would be the second element of this. And eventually you have a rectangular view of this multiplication. You would have 8 rows and 6 columns, or in this case, 6 rows and 8 columns. This is commutative, it doesn't actually matter which one we do. But that would be the definition of the multiplication. It's very similar for nested loops. It's saying for each pass through the outer loop, do the entire inner loop. So for each pass through this, do all of this work. So we're repeating all of this work for each of the 8 times. So it's exactly the same logic, and that's what allows us, we're going to consider every single element in the matrix. And we need to do that to calculate the sum. The sum is going to be updated once for every row column pair. But now imagine that these loops were sequential. So we wanted to do something for each row and for each column, and not both at the same time. Can anyone come up with what that image might look like? So let's say we have the matrix here. The nested loops says we're going to make a check for every single element in this matrix, however long it happens to be. We're going to include something for each of these elements. If these loops were sequential, how much work would that be, and how would you represent it in this matrix idea? We would be doing something once for each row, and something once for each column. Does that make sense? If these were next to each other, we would be iterating the first one once for each row, and then the second one once for each column, rather than for each row column pair. So this is quadratic, and this is linear. Does that make sense, the difference between the quadratic and the linear there? Because this is basically rows plus columns. This is R plus C, and this is R times C. So whenever you have a loop followed by a loop, you add their associated complexities. So we add the associated complexities. Whenever they are nested, we multiply their associated complexities. Now, just because we are multiplying does not necessarily mean that it is quadratic. That's only the case if each of the outer and inner loops scale with the size of the input. So does it make sense that we can make a matrix that has more rows or more columns? Yes, they both scale. Whereas with the previous example, where we were doing something in a loop exactly 7 times, that's a constant. So instead of having R times C, we would have something like 7 times C, or 7 times something, it becomes a constant that we ignore. So you need to make sure that you are looking at the loop and determine, is this being done a variable number of times or a constant number of times? So you can't just look at the number and form of the loops. A form is probably, you do want to look at the form, but you can't just see that there are a loop inside of a loop, it must be quadratic.
Can you explain why for the for loops, it'd be n+1 again, instead of just like it iterates 10 times, it's starting at 0 and it's like.
Yeah, 0 less than the length. This is done because we're gonna do this one more time. We're gonna bump up the I++ before we fail for the last time. I think that's why. Does that make sense? Any questions about this logic? I think this also helps you to visualize linear versus quadratic. This is kind of 2 times, this is as many times as needed. Cool. We good with this? Can I erase it? All right. I said yesterday that I would talk about the difference between theta notation and big O notation by the end of the class. We didn't quite get far enough, but it is time now. I will start with a really weird question for a computer science class. Are you more of an optimist or more of a pessimist? Take a second to think about it. Who here would consider themselves more of an optimist? And who here would consider themselves more of a pessimist? It's really funny that it's just about half and half. When we're doing computer science analysis, you're going to have to play the role of a pessimist way more frequently than an optimist. And as you start to do this, you will probably find that even if you think you are an optimist, 10 years from now, after analyzing computer science for a long time, you will become a pessimist. Maybe not. But I like to kind of make the parallel between optimism and pessimism, and also algorithm analysis. We can take an optimistic approach and say, well, if everything aligns perfectly, here's how long this algorithm will take to run. We could take the pessimistic approach that says, if things don't align at all, in the worst case, how much work do we have to do? So we can think that an algorithm may have vastly different performance based on how the underlying data is represented. We will start by imagining that we're going to sort a list. We have a list, it's in some order. What do you think the order would be in order to create the least work in order to sort it? What that means is, let's say we have an array of 10 elements with the values 1 through 10. How could you arrange those values such that it would take the least work to sort?
These are already sorted.
Already sorted, it's already in order. That seems like a good call, right? You just have to verify that it's in order, and then your sorting work is done. You don't actually need to do any of the work to sort the list, you just do a verification. So yes, if it's already sorted. What would create the most work to sort it?
Sorted in the opposite order, it's supposed to be sorted.
I like, both of these are very good ideas. So the competing ideas are if it's reverse sorted or if it's in a completely random order. Think about that for just a few seconds. Which one of those might be algorithmically more challenging? The answer is, it actually depends on the sorting algorithm that you use. If you use one method, one of them is going to be the worst case. If you use another method, the other one's going to be the worst case. So there's no actual 100% of the time right answer. But in general, I will think a random order with nothing in its correct place might be the most work, but that does not mean that reverse sorted is the wrong answer. We will find an algorithm within the next week where that is the worst case. Then we can think, on average, how much work can we expect if the list is in a random order? That one ends up being really difficult to answer most of the time. And in fact, for some algorithms, we don't even know. No one has ever proven on average how much work it's going to take with mathematical notation. So we usually have to pick between the optimistic approach and the pessimistic approach. Do we want to report, well, if everything aligns perfectly, here's how long it takes to run? Or do we want to report, in the worst case, here's how long it takes, it probably performs better than that. Worst case is so much more useful. It gives us an upper bound on how long something is going to take. It may be better than that, but it allows us to say it can't be worse than this. Whereas the best case may be cherry picking something that is never actually going to happen, and we don't know how much worse it is going to perform on average, or in the worst case. That is not to say those of you who raised your hands and said you were an optimist are wrong. I very much admire optimists and wish I could think the same way. So in computer science, just take the role of a pessimist, and we are most frequently going to use the worst case analysis. So you can think, hey, it can't be worse than something. So let's take an example. The array list contains method. This determines, with given a parameter, whether or not the array list contains that element. So we could pass in to an array list of integers 12, and it would go through and check, is the first element 12? Is the second element 12? Is the third element 12? Is the fourth element 12? So here's exactly how this would work. Here's the contains. We're going to loop through the size of the list. And if we ever find the element, we're going to return true that it contains that element. We don't care where it is. We just care to return true or false the list contains it or does not contain it. If we get to the end of the list, we'll return false, the list does not contain the query. Questions on contains? I will ask then, what is the best case scenario? The very first element, right? It takes the least amount of work if we do this. If we were to ask what is the runtime order of the best case scenario, what would that be? Does it matter how long the list is? In the best case, if the list is 10 elements, in the best case, it's in the first position. If the list is 1 billion elements, in the best case, it's in the first position. It doesn't matter. Is this what we would expect, though? No. So reporting the best case isn't particularly useful for something like contains, because when we think about what is the expected behavior of contains, we can't just make the assumption that it's always going to be in the first position. So in this case, the best case is constant. Theta of 1. What's the worst case scenario? It's either not in there or it's in the very last element of the list. Either one of those would take the same amount of work. What is the runtime order of that? Yeah. So if the list is 10 elements, we're going to say is in the first position, second position, third position, all the way to the 10th position. And then we would return either, yes, it's in the 10th position, or no, it's on the list at all. If the list were a billion elements, now suddenly it takes a lot longer to loop through a billion elements and tell me, no, it's not on the list. So what is that order? Theta of what? N. So we see that there's a big difference here between the best case scenario and the worst case scenario. But now we've also created mathematical bounds. We know that if we call contains, it's going to take some time between constant and linear time. There's no way contains can take quadratic time. Where exactly is it going to be between linear and constant? We don't know, but we have an upper and lower bound for it, which is very useful. How much harder is the question on average? How long can we expect it to take?
You say like n/2.
That would be kind of a simplistic way to do it. It's probably the best that we can do. But also think about, what if this list contains only the numbers between 1 and 10 and it's a billion long? It's likely that we're going to find it before the halfway point because there are multiple elements that are the same between it. So maybe it takes slightly less than that, but it starts to become problem dependent. It depends on the underlying representation. So we can't really easily calculate an average without more information. But maybe you would expect on average to be about half the size of the list. So we find that the average case is often more similar to the worst case than it is to the best case. What is the order of the average case? If we were to assume that we would have to, on average, iterate through half the list, what runtime order is that in? It is still linear. Divided by 2 is just a constant. So we can take it out. In this case, the average case is in the same order as the worst case and in a different order than the best case. So given that the average case is really difficult to compute, we have a choice between the best case and the worst case. We will find that the worst case will tell us more information more frequently than the best case. So questions on this before we move on to the actual notation for these? So now is when we get into the concept of big O notation. This is what is frequently reported and you may have seen before in terms of runtime analysis. So if we do a worst case analysis, we know the algorithm is going to take less than that amount of time or some constant scaling times that amount of time. So if it's linear, we know in the worst case, it's some constant times linear. It may take less time than that, but we've derived a worst case bound. So if you report big O of some function, that tells us that this is the worst case behavior. You use theta when you know the exact order. You say, no matter what, anytime this runs, it will always be in this order. It will never differ, it will never vary. That's when you use theta. I know exactly which order it is. If you use big O notation, that gives an upper bound. It may run in a lower order, but it will not run in a higher order. Does that make sense? So the contains method of the array list, you would say runs in big O of n, because it may just be that first element and returns it in constant time. But in the worst case, it has to iterate through half to the entire list, and that will take time proportional to the length of the list. So one way to think about this is the algorithm will run in time proportional to the order of f, order f, but it may also run in a lower order if the inputs are in a friendly underlying fashion. You may also want to report the best case running time. And if you do this, you can use big omega of f. And big omega just says that the algorithm cannot run faster than the order given. But it may also run in a higher order if the inputs are not particularly friendly. So you can think of this as mathematical lower and upper bounds for the algorithm's runtime order. I am likely not going to test people on what I am about to say, but it's also worthwhile just to know that there is also little o and little omega. And those become the strictly less than and strictly greater than. They're mostly used in algorithmic proofs to say, I have shown that the algorithm cannot possibly run in this order, but it certainly runs in a worse order than this. So you get the strictly greater than and strictly less than from little o and little omega. So the capitals just mean less than or equal to or greater than or equal to. And those are the ones that are very frequently used. Questions on these? All right, it is time for our epic battle. We are going to pit the array list against the linked list. With all of the information that we've covered, we have the information that we need to determine which of these is the superior list. Should people use an array list? Should people use a linked list? So we want to compare how each method of each of them are going to run. So let's start with the add method. Thinking about how an array list adds, and assume this is adding at the end of the list, and how a linked list adds at the end of the list, what is the runtime order associated with this? For the linked list, you can assume that we have a tail pointer. Is there a difference? And if there is, what are the associated orders? If there is not, what is the single order for both for add?
Well, the array list is fully at a top, the list is something quite big, right?
That is very true. So we would actually have to get into this concept of amortized analysis, which I don't really want to get too deep into, but that concept basically says the worst case would be we resize every time, but that's not going to be the case in the long run. So amortized says if we did something like add repeatedly, what is the cost of the average add? So let's say we double our list from size 4 to size 8. We get 4 adds in constant time before we do something that is linear, but is also proportional to the number of adds that we just did. And you'll find that the average add takes time too. So it actually is constant time, but it is a very good point that in the worst case, we do have to resize, and that resize will be a linear time operation.
Use an array list because for the linked list, if you insert or if you add an element, it adds it to the end. And
If we have a tail pointer, how much work is that?
Oh,
Yeah, we just follow the tail pointer, make a new list, and we have a single thing to do. So both of them actually end up being constant. So there is no benefit to using the array list or the linked list when we are adding. Note that if we have big O of 1 and big O of 3, something like that, it's not enough to gather. How about remove? Yeah, we'll say that we're removing, well, let's say that we're not. Let's say that we're removing from somewhere arbitrarily. We pass either a value that we want to remove.
Probably the same, right? Like linear, modal. You get the cycle. There's no index given.
Yeah.
Just the element.
Yeah. If we're removing the beginning element, how difficult is it?
Constant.
Constant for. So let's say, this is a good question. We have an array list. And these have values. We want to remove the first element. What needs to happen? What should the end result look like?
Oh, you have to copy the list, don't you?
Yeah, we have to start moving, we have to move the 2 over here, and the 3 over here, and the 4 over here, and the 5 over here. So removing is actually quite painful in the array list. When for the linked list, as long as we have access to the node that we want to remove, we just modify a couple of pointers. So it depends where in the list you are removing. How about get? Just returns it without modifying it. And the last one we care about is contains. Tells us whether a list contains an element or not. Linear. So here's the actual table. So removing from a linked list is going to be constant. And getting from an array list is going to be constant. For add, they can say. For remove, now it starts to be difficult. So we start to get a sense of there are strengths and weaknesses associated with each of these. So rather than there being a winner for this epic battle, we need to think now about what operation are we more frequently doing? If we are more frequently removing elements than just getting them, if we're actually trying to take them out of the list, then we will prefer a linked list to an array list because the amount of time that it takes to do this is significantly faster. If on the other hand, we just want to go get an element, then the array list can just teleport into the list, grab it, whereas the linked list has to iterate through the list to go find it. So that gets bonus points to the array list. It's faster. If one of these were just strictly better than the other, we wouldn't teach the other one. Both of these are frequently used because depending on what you want to create a different kind of list. There is one other benefit to a linked list. Does anyone know what that benefit is? Yeah, store more what, sorry? Store more data. They should be able to store about the same. In fact, I think the array list will probably end up using less overall memory than the linked list. But let's say we're on a system with very little memory. Let's say we have, we'll just draw this, and we'll assume this is the entire system's memory. Yeah?
Does the array list have to exist like in a block?
Yes, that's exactly right. So an array list has to be contiguous. So usually somewhere in your RAM, you're gonna have the operating system taking up some amount of that RAM, significant amount of that RAM. You have some working programs. Maybe I have PowerPoint up, and PowerPoint is gonna take some space here and some space here, just whatever happens to be freely allocated. And now suddenly I wanna make an array list of size 10 billion. There needs to be some contiguous space in my memory in order to be able to store this. And you can't move around easily working memory and just make that take up a different place in RAM. So there needs to be that contiguous block. If you can't store it here, then you're going to get an out of memory error, even though you have the memory to store it. If you have a linked list, what do we know about how linked lists are stored? They don't have to be contiguous. We could have a node here that points to a node over here, that points to a node over here, that points to a node back over here, that points to some node over here, points to a node over here. They can exist all over the place. And as long as you only have enough space for a single element of the linked list, we can continue to make new nodes. So there is a memory benefit to using a linked list over an array list as well. That doesn't usually come into play unless you're dealing with really large lists, but it's worth knowing about and thinking about if that becomes a thing. I wanted to give one more graphic that just kind of in general shows you the actual time here doesn't really matter. It's more so the difference between them. So you can see that when you call an array list add versus a linked list add, they take just about the same amount of time. The gets are very different between the array list. The array list get is almost immediate. The linked list get takes a really long time. The array list remove, oh my goodness. This takes a significant amount of time, and a linked list remove doesn't, it still takes some time, but it's on average significantly faster than the array list. So of course, given this information, we can figure out when we care to use an array list, whenever we're going to have lots of gets without removes. So maybe this becomes like a database query where you're not writing to or getting information out of, like removing information from a database. If you have a huge database that is going to store some information that does not get changed, store it underlying as an array list. If you need to actually remove elements from it, now you want your underlying structure to be. All right, we're out of time. We're gonna come back tomorrow for one last day of this. It's probably not gonna take the whole class period. I really just have a little bit more practice for us. But then we're gonna transition into starting to sort and learn some basic sorts. I will see you tomorrow for that. I have office hours if you have any questions about the assignment. Starting right now in my office. Yes, that's exciting.